We have been talking about canonical distribution, and what we mean by canonical distribution is that we have a bath and we have a system here, and this system is connected to the bath, and let us call this system as A, and let us say this is A prime and say this is A naught. So, our system is A, which is allowed to exchange energy with A prime, and A prime essentially consists of several copies of A itself, and so these members of the ensemble, they exchange energies with each other and come to an equilibrium temperature T. And so, this A0, which is a combined A and A prime, that is considered as an isolated system. All right. So, what we have derived is that what is the probability that our system is occupying a certain energy level E r, and this the normalized probability is given by exponential beta E r summation over r exponential minus beta E r, and this denotes the probability of that our system, which is A, occupies or is found in one of the available energy states E r. Okay. So, we will carry out some very important calculations, but before that let me give you a glimpse of what is called as a central limit theorem. I will not go into details of that, just give you the statement and tell you what a normal distribution is. So, central limit theorem, it states something. So, you consider m statistically independent observables, which are O I, and then the theorem states that the probability density of the observable O Q P is normally distributed. So, how is O Q P, which is the observable, how is it defined? It is defined as sum of all the observables, which means that if I denotes the index for the observable. So, this O Q P is actually sum of I equal to 1 to m and O I Q I P I. So, the main thing is highlighted here in italicized font, it is normally distributed. So, what is meant by normally distributed? So, any variable x, here of course, we are talking about two variables q and p, but nevertheless they are independent variables. So, this variable x is said to be normally distributed if the corresponding probability distribution that takes a form which is given by this 1 over 2 pi sigma square and e to the power minus x minus x 0 square by 2 sigma square. I think there is a square root there. So, that tells you that this is called as the normal distribution. It is also called as the Gaussian distribution. So, normal, Gaussian, and often it is called as a bell curve or bell shaped curve. So, as you see that so the mean is at x equal to x 0. So, this is x, this is x axis and this is your rho of x. So, it is peaked around some value which is at x 0, and then on both sides of x 0 it falls off symmetrically. And the first moment of this distribution, what I mean by first moment is that you have a rho of x and from minus infinity to plus infinity, this is called the first moment of the distribution, and this is equal to x 0. So, integrate over all x. Okay. So, this is equal to x 0, and if you take the variance, this is called as the variance, which is the average value of x minus x average whole square, and that gives you a sigma squared. So, this is like the this variance, this is the full width at half maximum called as a sigma. So, if you look at this distribution, let me sort of move this somewhere else. So, nth moment of the distribution is written as x n rho x dx from minus infinity to plus infinity. Say a teacher tries to analyze that after the end term examination or the final examination, he starts analyzing for a large number of students in the class the marks that they have gotten in a particular subject that he or she is teaching. Now, you see that there is a mean there. So, there is an average value where most of the students are the number of students getting mean value or the average value is maximum. As you go away from the maximum on both the directions, the number gradually comes down. So, this is showing a histogram. So, between say 70 and 80, you can think of that this is probably a 150 mark question paper, and it so anybody who's getting 0 to 10 is not there. So, there is no one who got 0 to 10, and similarly no one got between 140 to 150. And as you see that the number of students doing very well and doing very poor, these numbers are very small, and the distribution of the marks obtained by students basically it is distributed like this, and there is variance that we see which is called the full width at half maximum. And the better the distribution is, which means the smaller this sigma is, it's likely that the teacher has done a good job in terms of setting his question and teaching, because you want these curve to be as sharp as it can be for a given distribution. All right. So, we will get back to the canonical distribution, and we will ask this question: what are the average and most probable occupancies in a canonical distribution? And if you are wondering that how did the central limit theorem come, you will see that even this canonical distribution that we are talking about is a sharp distribution, and as you deviate from a most probable sort of values of occupancy, then the distribution very quickly tapers off, and that's the whole idea. Okay. So, we consider an ensemble of say identical systems. So, there are n identical systems which are members of the ensemble, and this has a total energy of this system is E. Okay. And ER is the different energy levels . And with occupancy NR. Okay. So, what it means is that these available energy states of the system they are occupied by NR number of particles. So, E1 has N1 number of particles and E2 has N2 number of particles. Now, this 1 and 2, these are dummy indices. So, you can assign any number of particles to any energy level, but subject to the constraint. So, the constraint conditions is that the total number of particles is constant. So, N R sum over R should be equal to capital N, which is the total number of particles, and not only that, because the total system, or rather the combined system A and A prime, that is isolated or rather insulated from the surroundings. So, we can have these ER NR equal to E. Let us call this as equation 1. And these are the constraint conditions that we have. So, any set NR that satisfies 1 basically that's is a possible mode of the distribution. What I mean is the following. So, let us consider 3 energy levels. Okay. So, these are E1, E2 and E3 and we have 10 particles. So, what we can do is that we can keep 6 particles here and 2 particles here and 2 particles here, or we can keep 3 particles here and 4 particles here and 3 particles here. We can keep 8 particles here, 1 here and 1 here, and we can keep 4 particles here, 4 here and 2 here, and then there are a large number of ways that we can distribute 10 particles in 3 available energy states. Now, all these are going to contribute to this to this distribution that we are talking about, subject to this constraint which is 1. Now, you see the constraint is 1 because the total number of particles is 1, and then we have not told you what are the values of ER, but we can always have values of ER such that we get a total energy E. I haven't specified what total energy is, then we have to multiply these numbers and see that they have the same value. So, all these may not be possible if you further specify E1, E2 and E3 their values, because you have to multiply the number of particles with that value of energy, say in joule or in electron volt, and then get the same number. Anyway, so you have a very large number of possibilities to achieve this constraint condition by distributing your NR number of particles among ER available energy states of the system. Okay. And the way this can be done, so the different or the possible modes of the system or the possible modes of this distribution are, we can write it as this, and we will write it as this curly bracket NR. It means something. So, we have N1 factorial, N2 factorial and so on. So, this is the different possible distribution or possible modes that this assignment of particles in different energy levels that can be done. Okay. Now, all these modes or all these possibilities are equally likely to occur. Having said that, it is also true that for getting fixed values, fixed values for the thermodynamic parameters, it is important that there is a most probable distribution among all these equally probable ones as well. I mean, what it means is that not all of them contribute equally to the distribution. There is a few distributions or a large number of distributions which are more important than others, because that assignment of particles in different energy levels, that is going to give us the value of pressure, volume and temperature, or whatever thermodynamic quantities that we are considering. Okay. So, out of this distribution, let us say that there is some distribution which is most likely to occur. So, once again I repeat that even though each of the distributions that we talked about, like here, say for example, all of them are equally likely to occur, but maybe one that you see here, okay, I mean here means this distribution, okay, not this one, this distribution may be more likely to occur, or it is a more probable distribution, and these distribution is going to give me the thermodynamic quantities that are measured in experiments. Okay. So, what it means is that this gives us this WNR star is maximum. So, that mode is maximum, or that comes with the maximum frequency, and we considered that distribution of particles to be a particular distribution NR star, And the assumption, or rather a priori, I can tell you that this is the distribution that is most important, and as you deviate from this distribution, the other possibilities of W NR, those contribute very little to the problem. Okay. So, the distribution is sharp, that is what is most important. Okay. All right. So, now let us calculate the mean value. Let me go to a new page. Mean value of different distribution sets. All right. So, what I mean by this is that what is NR? That is the average value of the distribution. Mean means average. The word mean, whenever you see that, it means average. Okay. So, this is what we want to calculate, and we know the weight. Weight is given by WNR. So, we have these sum over all these NR possibilities. When I write it in a curly bracket, which means it takes into account all the possibilities of NR to be distributed in different ER energy levels. So, NR, W of NR and sum over NR and this weight itself. So, this is a definition of average value, and we have told this a number of times because this is a weighting factor. This mode or frequency or the weight is given by W, and then you calculate the average by this. So, we want to calculate what is NR star, for which this W of NR is sharply peaked. It means the same thing, that what is the most probable distribution of particles. Okay. So, what we do is that we are going to minimize this. Minimize this means minimize this expression, which is expression number 2. So, how do we minimize certain thing? We take the derivative with respect to the parameter that is being varied and see that, put that equal to 0, and then calculate how that is for what value of NR star this has a maximum. Okay. We can actually check an extremum, but most of the time that we take a derivative, it gives you either a minimum or a maximum, and in this particular case we are interested in the maximum. If you really want to see that it is maximum, then you have to take a double derivative, and that should come out as negative, because the distribution should be curved such that as you are at the top of the distribution. So, you actually, the curvature gives you negative for a maximum value, whereas for a minimum value the curvature is positive. Okay. Anyway, we will skip that discussion for now, and what we do is that we sort of write down the log of this distribution. In fact, taking a log is better, and this is equal to, so if you look at this 2, you see, so it is a log of n factorial minus log of n1 factorial minus log of n2 factorial and so on, and then we will use what is called as this Stirling's formula in order to calculate these quantity. And you will see that a bit of simplification is possible here, and what one gets is that log of W is equal to n log n, NR log of NR. Okay. So, for each one of them, so R goes from 1 to n. Okay. Now, when we try to take a differential of this, that is how it changes as NR is slightly varied. Okay. So, which means that what happens to W when NR changes from NR to delta NR. That is, a little bit of change occurs. Let us see how that changes, and that can be calculated. So, it is a delta ln W. Now, if you take the first term, the delta of the first term, that is equal to 0. So, we will not write that, but now we will write this as NR plus delta NR and log of NR. Now, I have only taken this derivative, or we can simply subtract this. So, we will have, so we just take a small derivative. So, keeping the derivative of delta NR, or rather differential of delta NR, not derivative, the differential of delta NR, log of NR, and then we will keep the delta NR to be constant and take this derivative which gives us NR of, take a derivative of log of NR with respect to NR. So, this will give this, and so we land up with a simple formula which is equal to a sum over R delta NR log of NR plus 1. Okay. So, that is the small deviation of the distribution because of a small change in the particle number in each of the available energy states. Okay. Now, this is subject to the fact that because the total number of particles is equal to a constant, so delta NR should be equal to 0, and not only that, you should also have ER delta NR should be equal to 0 because of this small change in the number of particles that we consider, because the total number of particles is constant, the total energy is constant. So, this has to be in conformity with this, with these two conditions, constraint conditions. So, now what happens is that what we do is that let us call it equation 5. So, we will put delta log W equal to 0. Why do we put equal to 0? Because we want to extremize the distribution. So, we will put that equal to 0 subject to these conditions, and that can be done by introducing two Lagrange's undetermined multipliers, one corresponding to the total number of particles being constant, the other corresponding to the total energy being constant. So, this condition that delta ln W equal to 0 is nothing but this is equal to a minus. So, this occurs for NR equal to NR star. Okay. So, this gives us this is your log of NR star plus 1 and minus alpha and minus beta ER and a delta NR equal to 0. I just want to draw your attention one more time. Here we had only this term, we could have put this term equal to 0, but this term is not an independent condition. It has to be satisfied along with the total number of particles being constant, which means the delta NR has to be 0. So, this sum that you write here or that you see here is not an independent sum, but it is subject to these two conditions which are written here. So, let me write them as equation 6. This is say 6a and 6b. So, this is equation 6a and this is 6b, and this is because of equation 6a and this is because of equation 6b that we have two Lagrange's undetermined multiplier. They appear there along with the other things, I mean the original the expression that we had, and now we have written NR equal to NR star because this extremization occurs at a particular value. So, when you put that equal to 0, so then NR becomes equal to NR star. All right. Now, for satisfying this equation which has a right hand side equal to 0, the only way that it can be done or that it can be satisfied is that you can write down this the term in the curly bracket to be equal to 0. There is no other way, because delta nr is arbitrary, that delta nr is not equal to 0. That is any arbitrary small number in, that is a number fluctuation in the number of particles in each energy state. So, we write this as nr star is equal to minus alpha plus 1 minus beta ER. This alpha plus 1 can be taken as a new constant, and we can write it as alpha prime, but there is nothing very sort of sacrosanct about alpha and alpha prime. So, we will keep writing it as alpha. So, which means that the nr star becomes a constant and exponential minus beta ER. So, this alpha plus 1 becomes a new constant, and then everything put together, I mean this C is the constant for. So, what it means is that we have been able to find a distribution of particles which is most likely to occur, and this is most likely to occur so that we get the equilibrium thermodynamic quantities, you know, as outcomes of experiments. Okay. So, nr star, which is this most probable value. So, nr star is the most probable I mean number of particles, or that maximizes the distribution W. Okay. So, nr star by n, this is equal to exponential minus beta ER and divided by sum over R exponential minus beta ER. So, we remind you that this is what we got as the number of this probability density that our system occupies a given energy state, and this comes out same for the average or the most probable distribution where this nr number of particles will populate energy level ER. Okay. All right. So, this gives you the internal structure of the gas, that is, this gives you how many particles are going to be there, was the most probable distribution of the particle. So, this gas comprises of the particles distributed in this particular fashion. So, once we have calculated the this average occupancy, we can call the average energy per particle, that is easy to calculate now. So, this is per particle, and that is equal to E over N. So, E over N is again has to be calculated. So, let us call this as for example, let me call this as U. So, E over N equal to U, which is nothing but equal to sum over R ER into this probability density exponential minus beta ER and R exponential minus beta ER. So, this gives you the average energy per particle, and this beta is nothing but equal to 1 over kT, which is what we have said. So, that is called as the inverse temperature, K is the Boltzmann constant. I write it with a sub B, so that if there is any other K, you do not get confused with that. All right. Now, this easier way of, or rather little manipulation can be done in order to write this. So, this is a del beta of log, and then there is a sum over R exponential minus beta ER. So, that is the expression for U, and this is an important expression, that is for the internal energy of the system. Let me write this as equation 7 and this as equation 8. Okay. So, this is the internal energy of the system. Now, what is more commonly used in these canonical distribution or discussion of in the present context is that there is a Helmholtz free energy, which is nothing but U minus T S. Okay, and this is equal to, so if you take a df, so this becomes equal to du minus TdS minus SDT. Use the first and second law, du equal to TdS minus PDV and minus TdS again minus SDT and so on and so forth. So, TdS will cancel out and you are left with del f df equal to minus PDV minus SDT. So, that gives you S is equal to minus del f del t N and V. Of course, it gives you other definitions such as pressure, etc. So, pressure here is equal to minus del F del V and N and T. All right. So, this is what we get and we have already gotten internal energy expression. Now, what you can do is that you can write down this U is equal to F plus Ts, which is equal to T minus T del F del T, that is replacing the entropy, it is N and V. There is a little bit of algebra or other manipulation can be done. There is just a mathematical manipulation to get an expression, closed expression for F. So, this is equal to del del T by F of T. So, you can easily prove that this is equal to the line that you see above. Sorry, this is F, not T, F minus. So, it is F minus T del F del T and so on. And this is again del of F by T, del of 1 by T. Okay. And again, you can just check these things, these are very trivial steps. And because your beta equal to 1 over kT, your F comes out to be equal to minus kT, and then I mean this is nothing but equal to this expression that we have written earlier, equation 8 minus dd beta of log of e to the power minus beta ER, and there is a sum over R there. Okay. So, you can compare these two equations, say these I have written this. So, it is easy to see that this is equal to log of sum over R e to the power minus beta ER, and this is a very important expression in canonical distribution. So, this is the free energy, Helmholtz free energy in the canonical distribution, and so we can define a quantity called as Z called as partition function. So, define this, and I will write it n just to make sure that this is for constant n, that is the number of particles not being exchanged, and it is a function of V and T, which is equal to R exponential minus beta ER. So, this is called as the partition function or the canonical partition function, and this partition function is a central theme of discussion for quite a bit of discussion that would follow. So, and this is so this is nothing but sum over R e to the power minus ER over kT, and the free energy is obtained from this, and once you obtain free energy then you can obtain a number of thermodynamic quantities. So, the trick is to first obtain, for a canonical distribution, first obtain the canonical partition function by evaluating this sum. We will discuss many cases in the coming classes, so that you understand how to evaluate this sum in a closed form, and in most of the situations that we deal with, there is a closed form for this sum is available, and once we get that, we can calculate free energy. From free energy we can calculate entropy, we can calculate for example F that is P, that is pressure, we can calculate specific heat, and we can calculate pretty much every thermodynamic quantity. So, we will stop here and we will continue with various examples, just like what we have done for the microcanonical case. We will talk about various examples to do with the canonical distribution.